Okay, hi everyone. Today we have two things that we talk about. The first one is that we say how to integrate over an arbitrary surface. So that will be the first part, integration over surfaces. And the second part will be finally there's some applications of these differential forms in terms of like frames. And like we want to adapt like a frame to a surface. And how do we use differential forms as one application to study surfaces and the geometry of surfaces. And we would like to start that kind of discussion today. Okay, so the first part is integration. And we have seen last... Okay. Yeah, it's not on. Like, I activated, but okay. Don't know if it's... Is it better? Okay. Yeah, if it's still too low, then let me know. I think always if I turn it up too much, then it starts to interfere again with the loudspeaker. Okay, so integration over a surface. So we would like to integrate over some strange looking guy. And last time, what we learned is how to integrate over a rectangular. So last time we studied like a rectangular, and it might be also like a bit of, like differently shaped. And the idea is to, if you want to integrate over a whole of surface, then we patch the surface together by looking at multiple of these rectangulars. So the idea is to kind of dissect your surface into areas. Where each of these areas is now a nice rectangular. So we can integrate over this rectangular, over this and this. And then you would like to sum up all the contributions that you get from each of the rectangles. So that's the idea. So first of all, it might happen that you need like infinitely many such rectangles. So for example, if I look like at the plane that starts from here and goes up to infinity, if I only have like finite size rectangles, then I need like infinitely many. That's like makes sense. So the first definition is that we would like to look at a certain kind of surfaces where we only need finitely many. And such a surface is called compact. Find like finitely many rectangular regions or images of finite number. It's important that it's finite. Rectangular. So if it goes on like for infinity, then you might be still able to tell like what kind of, like what is the integral, but then you have to worry about like convergence at like infinity. That's like typical things. There's like the integral from a to b, where a and b are finite numbers, that's relatively simple. But if you look at an integral of that form from a to infinity, then you might have like to worry about what happens at infinity, and the integral might not exist. So that's why we essentially look at like the finite version where we only have like finite numbers, and that's encoded in this finite number of rectangular regions that we need. The second thing is that we have to worry is that essentially we don't want like to count, for example, contributions that come from such an edge twice. So we would like to say in some way that, for example, if you walk around, like in this particular orientation, and if you then would like to walk around the neighbor rectangular in the opposite direction, so that like or maybe it's so for example, assume I want to calculate integral over this blue rectangle. What I can do is, of course, I can dissect these two things, but I want that these boundary terms or the boundary conditions of like this in the middle one, like exactly are opposite to each other. So otherwise, I count that essentially twice. So for that, I need to make sure that I walk around this. Like I can think of the orientation of this one particular rectangular as like saying what is the orientation of the boundary, and then I need to make sure that that I walk around like this other rectangular in the opposite direction. You see, like here, one of them is like walking downwards, the white one, and the green one is walking upwards. So that's like I need to make sure that the orientation of these edges are like opposite to each other. So that if I, for example, have an exact form and I integrate it over the blue thing, then I get like that it's like the contribution on the edges. And if I make sure that the edges are oriented in opposite ways, then this contribution will like cancel each other. So that's one way that I have to. There's something that needs to be addressed, and it is like related to this orientation. And the first thing is that that on each of these rectangles we have like two options to define an orientation. So each of these rectangular regions are has an orientation. Which we can think in two different ways. In two different ways. So the first one is what I already described, is that we have like an orientation of the boundary curve. So that's the first one is an orientation of the boundary curve. So it's just saying in which way I walk around the rectangular. I essentially have two choices, right? I walk either counterclockwise or clockwise. That's like the two options. And a different way is that we can also think of that as a normal vector that points in a certain direction. In this case, we have a normal field, which we can calculate by this vector where we get like, remember I is a function of two coordinates. We can take the derivative in the x direction to get for each point a vector. And then we take the cross product with the same vector in the y direction. So that's a normal vector field. And you can think of that as like giving you some orientation as saying that it's like pointing outwards. And of course there are also like two ways to define an orientation. I can just like, for example, flip the x and y direction, and then I get exactly the minus sign, like the opposite direction. And they are related, both of these like different ways to orient a rectangle are connected as follows. Namely by the right-hand rule, essentially. So we have the rectangular, say we walk around, the orientation is like defined in such a way. What we do is then we take the right hand, say the thumb should be pointing in a normal direction. So and we want to make sure that the orientation of the boundary curve is correct. So what we do is we point the thumb in the normal direction. The index finger goes in the direction of the boundary, and then the middle finger should point like towards the interior of the rectangle. So in this case, it's true. Like we have the index finger is pointing outside, out of the plane of the blackboard. Then here we have the index, and then the middle finger is pointing towards the interior of the rectangle. So it's like in all of the sides, it's always the middle finger pointing into the interior of the curve. It's the interior of the rectangle. So let me write that down. It's like right hand. So that's the thumb. Is in the normal direction, the index finger direction of the boundary, and then the middle finger should point in the interior. So that's the, like essentially I have two ways to think of like this. Either point it like as a normal direction which says, okay, this is outside and that's inside, or reversely I can like just like fix a boundary, a curve, and it gives me an orientation of like a rectangular piece as well. And both of them are connected. So if I give you the normal field and say that's outwards, then you can like derive like the orientation of the boundary curve and vice versa. So that gives us two different ways for orientation of a surface in a very similar way. Similarly, for a surface, for compact surface, we can think of some subset of R3, an orientation is one of the two datas. I will think of that as a differentiable field of vectors of R3 on S, which are not necessarily tangent, and we want that to say that it's nowhere vanishing. So again, that's like we have just like a surface. Select the. So you can, for example, take this base cap. That's our surface, and now we have to say what is the inside and what is the outside of that surface. So we can either say, let's say we take this the green thing as like this vector field n, which is then just pointing like in a continuous way in a certain direction. And then we say that's the orientation of the surface, is just pointing outside. And I can, of course, take the opposite direction, in which I would say this one is outside. So it's like the same surface, but just inside out. And then like that one would be the outside. But like, you know, if I turn it around, then it won't pointing directly in the opposite direction. So that's the normal vector field you can think of like as a surface, and then at each point you have a certain direction that says that's outside, in which it's pointing. So that's the one way to define it. And conversely, we have can also say it as a decomposition of S into rectangular regions, and each one is oriented. Such a way that the boundary curves are common. Boundary curves of the opposite direction. So that's what I like was explaining here, that we want like to have like these boundary terms of each of these rectangles in the opposite direction. So say I have to walk in this direction now here, and similar, we can continue then automatically in this way. And then we by the right-hand rule, that would correspond to this one in a normal direction, this one along the boundary, this should put inside, so the normal vector field is like pointing outwards. It's like the normal vector field is pointing outwards, and then you can like determine the orientations of all of these other rectangles. So that's like the orientation now, and we worry about orientation because, of course, like you know that for an integral, what we have is that if you integrate some function from a to b, then that's the opposite term as from a to b. That's something that you learn very early in your education, and that minus sign is like something that we have to now choose very consistently. Otherwise, we get like things that like don't add up in a meaningful way. So that's why we have to worry about like finding a and b in a consistent way, so to speak, on a surface. And then an important result, or like an important thing to notice, is that not every surface has an orientation. Not every surface has an orientation. That's important. For example, we had this example, I think it was in one of the homework exercises, where you were looking at the Möbius strip, which was like a long strip. Then you twist it once and then you glue it back to each other. So that's like, so you can't do that with a sheet of paper because it's too short. But if you have like a long strip or a narrow strip and you turn it around and then you twist it once and then you glue it back, there's like no way to orient that. So in a meaningful way so that you get like a differentiable field. It would always jump at one point because if you go around then you end up in like the opposite direction. So example of a surface without orientation is the Möbius. So we see we have like two ingredients essentially that we need to worry about on a surface. One of them is that we only want finitely many rectangular regions. So that's the compactness that comes in there. And the second element is that all of these regions have to have a nice orientation which is compatible. Then we are able to define the integral of the surface, which is saying that force S is a compact oriented surface. State of like decomposition. Finally, many rectangular regions that we get, and beta is a two-form on S. Then the integral over the surface of beta is defined as we take the integral over all of these rectangular regions, integrate beta, which we can, that was like something that we defined last time, how to make sense of this integral over a rectangular region, and then we just sum up all the contributions from all the different rectangular regions. So that's the definition. Integral of beta over S. And the first question that you have, and which you can answer positively, is like, does this contribute, like integral the right-hand side? Does this depend on how I like dissect the surface into different rectangular regions, right? Like it's like here we have just one decomposition, but there might be multiple ones. You might, for example, cut like one of the rectangulars again, or like move them around a little bit. And the first result is, which I don't want to prove, is that this right-hand side is actually independent of the way that you cut your surface in I. So that's like a remark. This integral does not depend on the chosen decomposition. So which decomposition you choose then, of course, depends on your applications. You usually take it like big enough that it's still a rectangular, and covers as much space as possible so that you don't need like many integrals that you have to calculate, but yeah, just like one big integral, handful of integrals. And the first result about like integration over surfaces is the following theorem. It's usually called Stokes' theorem. But actually Stokes, as so many theorems in mathematics, is like a completely misnomer. There were, I think, like 5 or 6 people contributed that to this kind of theorem. And Stokes essentially just like, yeah, like didn't do anything like meaningful in the way of proving it. What he was doing, he put it as an exercise or like a problem in the administration test for like Cambridge. So if you wanted to attend Cambridge, you had to take an exam at the beginning. And Stokes was one of the guys organizing that exam. And he said, okay, let's put like a proof of that theorem as like the like the test that you are that you get like admitted to Cambridge. So that was like what he did with that theorem. And the theorem is like something that you can guess, namely for any one form alpha on S on a compact oriented surface S. Where the surface may have a boundary. And we want that boundary curve to be oriented in a way that is consistent with this decomposition. For example, here we have this part is like walked around in this direction, so then this part of the boundary is walked around in this direction, and now we continue in every direction. So we see, for example, here we have like some over orientation and they are consistent. So it's like once you fix essentially one orientation of a rectangular, then it gives you an orientation of the boundary term. So that's like with a boundary and then oriented. By the decomposition. And then the result is the following, namely that the integral over the surface of the exterior derivative of alpha, which is now a 2 form, and we can integrate over that over the surface. And the result is that we can write this as the integral over the line integral over alpha over the boundary of the surface. So I erase the blackboard, and then we will see if you're good enough to be admitted in Cambridge and you can give the proof. Very simple. The idea is essentially like this part here. We just like dissect, we go back to the definition, which means we have to calculate these RIs. There's no way around that. And then on each of these RIs, we can use the Green's theorem from last time. We calculate that as a boundary integral. And then because these boundary terms, like of common rectangles were walking along the different directions, they always cancel. And the only contributions that we get are like things that are the outside, which don't have like a common partner to cancel. So the proof is apply theorem rectangle. So what we get is then that the integral over the alpha equals the sum over integrals the alpha, which we can then write as the integral over Ri of alpha. And now we observe that the boundary contributions common boundaries cancel out. So it's like the idea is you have like at least if you have a common boundary term, then you have like then this boundary occurs at least twice in this integral, like in the sum, and then like once with the one orientation and once with the opposite orientation. So you get like always the same like the value, but with the opposite sign. So these cancel out, and then the only contributions that you get here are the integrations from the boundary outside, which don't have any other partners to cancel each other out. So that's maybe also why you see why we choose this orientation to be such that the boundary terms are like opposite to each other, right? Like you could also have maybe choose to define an orientation as something where you say like they have to agree. But if you say like they have to be agreeing on the boundary terms, then you just get here plus 2 times of the integral over the common boundary. So that's not what you want. And that's why you choose that like one of the curves goes in this direction and then the other direction has to be the opposite. And of course, this result is very powerful because it allows you to calculate certain integrals instead of calculating like essentially 2 integrals or like an integral over a surface, but we can reduce that to a simple line integral. That's usually very easier to evaluate than really calculating such a double integral. So the application to convert surface integral into usually easier line integrals. Sometimes it's actually the opposite, that you have a line integral, and actually it makes sense to look at that as like a surface integral. It's a bit like related to what you see in the complex geometry, where you have, like, for example, the residuum around a point. It's sometimes easier to write that as like a certain integral over like the whole thing instead of a certain line integral. So that's a bit similar, but usually what you really want is like to calculate the surface integral, and this theorem tells you one way to do that if your form is exact is by just converting it to the line integral. there are, of course, also applications in physics. I think Mr. Stokes was actually also partly involved in the study of like more applications in physics than for mathematics. And I just want to give you the flavor of that. So for that, look at the following example, which is Faraday's equation. And since we are now already know differential forms, I give it to you in a following form. Equals to 0, where E and E are time dependent one forms on some subset of our field. So that's Faraday's equation in differential forms, where you have a one form, here is a one form, and here is a two form. So you have a one form E, which is the electric field. You can write that in a certain form as a one form, and you can write the magnetic field as a two form. And yeah, like there is a certain way to assign that to these normal vectors that you know from vector calculus or electromagnetism, and that's one of your homework exercises, is to relate the normal calculus versions to this kind of equation. But assume that you did that, and now we can use this power of like the Stokes theorem to analyze that equation, mainly by integrate this equation. So we have like some surface. Then what we get automatically is that the integration over this equation we can write as the first part is like the integral over dE, which we can use with Stokes theorem to rewrite as the line integral along here. And then we get d of dt of the integral of b, and that's equals to 0. So we have some surface, and then say like ds you can think of as like some wire. So you have like a wire that is like makes like some kind of circle, and then the integral over that wire would be the outer integral, the line integral, is like the electric field induced, and B is like a vector essentially that goes through this field, so that's the electric field, and that induces some kind of electric field along the boundary. So you have like a magnetic field, and you have a boundary, and then if you have that magnetic field is changing over time, so you have like ddt is non-zero, what you get is some electric field in the boundary. So that's like very physically, right? Like it's like really like the Faraday's equation or like Faraday's law. It's exactly that. If you have a magnetic field that is time dependent, it induces electric field in the boundary. And that's like really just like an application of the Stokes theorem, and that we managed to rewrite Faraday's equation that is originally some vector form, in this case over here. Yeah. And in fact, all laws that you know about vector calculus, so Green's theorem, Stokes theorem, there was maybe a third one, always forget the names. Like all of them are like essentially a result exactly of that form. that you take D of a certain 1 form or 2 form or 3 form, and what you can write is that you get like one step lower. So that's essentially Stokes' theorem applied to different kind of forms. Okay, so that's all I wanted to tell you about, like the general knowledge, what you should know about differential forms. It's like we covered quite a bit of material. So it's like the wedge, product. We have discovered like the exterior differential, and now integration, and like shown that they are kind of dual to each other. So that's like the material that we know about differential forms, and now we would like to use them actually. So that was the main motivation for why we introduced differential forms, is to actually use them to study geometry of surfaces. And that's what we want to do now. Chapter will be a curvature of surfaces. So similar as with curves, we want to now say, like, what is the curvature of a surface? That will be essentially a subject, I think, like for the rest of today, definitely, and some part next week or so as well. So it will be quite some time. And the idea is essentially that we use the same trick as with curves, which was the Frenet-Serre frame, right? Like we had a certain frame that was adapted to the curve, and then we looked at like how that frame changes and like express the changes of that frame with respect to itself, and then these factors that we got were the curvature and the torsion. So we would like to do the same thing essentially as with surfaces. And that leads us to this idea of considering what is called moving frames. So that was like an idea that was pushed forward by Cartan, and goes back to Cartan. So we call that for curves, we had like two, we had a orthonormal basis, and every point of the curve, so that was T and B in general, which was adapted to the curve. Namely, for example, T was nothing else than the velocity of the curve. So that's like some connection of these orthonormal bases with respect to the curve. So that's like the starting point. And then the important observation was that the change of this frame expanded or expressed in terms of the frame again. Told us the curvature and the torsion of the curve. So that was Fourier equations, which told us like if you take the time derivative of t and b, we get like a certain matrix which were antisymmetric, and then the inner entries of that matrix were essentially kappa and tau. So that's what we learned in the first part of the course. And now we would like to do something very similar as we did with the curves, also for surfaces. Here. And so we would like to choose a frame, and that frame should be adapted in some way to the surface. And then we would like to express how that frame changes as we go along different directions. And from that equation, we want to say something like we want to calculate that change, and we want to express it in terms of the frame again. And then the coefficients should tell us something about the curvature of the object that we study. So that's the idea. And in fact, it turns out that it's a good idea to look at a very general setting where we forget about the curve and the surface in the first place, and we just look at the frame in itself, and then in the second step think about what it means to be adapted to something. So that's the strategy. It's frame from the constraint to be adapted. And then in the second step, we implement that constraint. And it might actually be looking a little bit foolish, because you can imagine what it a frame, the whole point of the frame was that it has something to do with the curve. So it looks a bit counterproductive, but the beautiful idea of Catan was that by just looking at the frame in itself, you get some kind of relations that are really powerful already. And then we so these are giving us a lot of structure already, and then it's only a little bit additional information that it's adapted to the curve, and that has some influences that we can exploit. So that's the main idea, and so we have to start with a general frame. They're usually called a moving frame. So moving frame. Say on an open subset of R3. We have some open subset